Hi everyone, and welcome to our first Docker Rosa meetup in 2021. This time we have a guest speaker, Chris Weichel from Gitpod. He's a chief architect at Gitpod and will talk about how Gitpod uses Kubernetes and yeah, runs his SaaS offering on Kubernetes and doing this with some special kind of isolation and rootless container, really good Linux-based and namespace-based stuff. Yeah, and Chris will give us a nice introduction today. So before we start, and I will hand over to Chris, just a note, Gitpod as well as White Duck sponsored some swag. So we would like to get a swag package. We have a small raffle. So if you have a question, please post it on Twitter, mention at Dr. Rosenheim and hashtag Gitpod. And if you do this, you will be part of the raffle and we will send you a nice package of our swag. So that's it. Thanks, Chris, for joining us today, and I will head over to you.
Yeah, thanks for having me. So yeah, welcome everyone. Today we're going to talk about Gitpod and how we made sort of Docker and containers happen within Gitpod workspaces. So first, what is a Gitpod workspace? What is Gitpod? So what Gitpod does is it provides automated dev environments in the cloud. And it basically takes all this setup pain away where before you would have a long outdated README file that you would have to follow before you could start working on any project. Gitpod basically turns this into automation. And you can get a new environment for the project that you want to work on with a click of a button or basically by pressing return. And all you have to do for that is you prefix any URL on GitHub or GitLab with gitpod.io/hash, hit return, and Gitpod will open a dev environment for you. And these dev environments, workspaces as we call them, this is the slide that shows that you have to add Gitpod in front. And these dev environments, or workspaces as we call them, are really Kubernetes pods. So for each workspace, we start a new pod at the end of the day. And what we really want is those pods to feel like your local machine. We want you to be able to do all the things that you would otherwise do on your laptop, except you get a new laptop for every task already set up with everything you'll need. And until recently, there were a few things that you just couldn't do. So for example, you were not root, right? These are containers at the end of the day and shared with many other or with a few other users on the same node. So one way of making that more secure is by simply not giving you root. And also, consequently, Docker wouldn't work. And this really is a deal breaker for some because a lot of our dev environments have already been set up using something like Docker Compose, or you want to run a Docker build as you develop. So what this talk really is about is how we made that happen, because now you can run something like apt-get install, or you can run Docker within your Gitpod workspace. So let's look at basically ways of how you could become root within a workspace container within one of those Kubernetes pods. And there is the very naive way that we could do this. And we could simply give you UID 0 within that workspace container. What that would mean, though, is that you'd also be UID 0 on the node. And as said, that node is shared with others and there are other services running on it. So you would be super privileged on a node. And this is not something from a security standpoint that we could possibly do or consider actually to bring into production. So we need a different way to make that happen. And this is where user namespaces enter the stage. And what user namespaces do, they're a Linux concept, much like all the other namespaces that basically make up containers. And what they do is they provide a mapping from within the namespace to outside of the namespace. So inside a user namespace, you can be UID 0, and outside of that user namespace, you can be something like UID 1000. And this also goes along with all the capabilities that you would expect to have as UID 0. So you get the full set of Linux capabilities within a user namespace. The thing is that outside of that namespace, they are not worth much because you're still attached to that UID, to that higher UID, and the kernel does well in checking sort of from which namespace those capabilities come from. So to drive that idea home, and when inside Gitpod, inside this user namespace, you are UID 33333. Outside, you are some other UID. You are not the one that you're seeing inside your workspace. So on the node, you are a different UID. And the same goes for root, right? So if you look at root inside the container, say we run this sleep process inside the workspace container, and we look at it from the node's perspective, then here you're also not root. You're also not UID 0. And it's exactly this mapping between UIDs and also GIDs that user namespaces provide. And this is what provides the isolation that we're looking for. So how do you get a user namespace? And this is just a rough sketch, but you basically call unshare to create the user namespace. And then you need to establish this ID mapping that basically says within that namespace, which UID maps to which UID or GID outside of that namespace. And you do that by writing to files in proc. And then you want to call execve afterwards to actually get all the capabilities, like once that mapping has been established, so that you get all the capabilities that you would expect to have now. You can actually try this yourself if you run this command. It's basically calling unshare minus uppercase U, which creates a user namespace, minus R, which maps your current user to UID 0 within that user namespace. And the strace in front basically traces the syscalls that are relevant here. This is all fine and dandy, except we cannot do this in a Kubernetes pod. And the reason for that is that in order to write to proc PID, UID map or GID map, we need cap sysadmin in the outer namespace. So we need cap sysadmin, in this case, on the node, because there are no user namespaces in Kubernetes yet. And this is exactly what we do not want. We exactly want to prevent having to give workspace pods cap sysadmin on the node. So we cannot simply create a user namespace inside the workspace or inside that pod and then write to UID map or GID map exactly because we do not have cap sysadmin. So what do? All this setup mechanism that creates the namespaces inside the workspace container, mind this is a regular good old Kubernetes container, we do in something called supervisor. And supervisor ring 0 is basically the root process PID1 that gets started as part of the workspace container. And then ring 2 is the process that also spawns the user namespace. And what we do then, once this process is running, we call out to a very privileged process on the node called workspace daemon that runs as daemon set on that node using gRPC. And we ask that daemon, workspace daemon, to establish this mapping for us. So basically we tell it within the container for PID2, please write these UID GID maps. And then daemon will do some sanity checks and will make that right for us. There's a problem though, because what we need to do now is we need to translate that PID2 from within the container to the PID on the node. Because workspace daemon lives in the PID namespace of the node, so the root PID namespace, we need to translate from the PID namespace of the workspace container to the PID namespace of the node, to the root PID namespace. And as it turns out, there isn't a syscall or something that we could do. There are some messages that you can send through Unix pipes that would do an automatic translation. The way we do it is we map this PID2 in here to the PID on the node by looking at what's in proc status. So if you look at the status file of any process under proc, in there you will find a field that is NSPPID, or NSPID, which lists the PIDs of this process in any PID namespace seen from the vantage point of sort of the caller, like whoever opened the status file. And because we know that ring2 must be a child of the root process of the container, if we know the PID of the container, we can look through all the children of this container process, and we will find the PID that we're looking for by looking at this NSPID entry in the status file of all the child processes of that container. So now we have a PID mapping, and we can write to proc UID map and GID map. Nice. So now we have a fully established user namespace. The next problem is that this works a bit too well. If we call unshare, have this setup user namespace, and now we look at our file system, none of this makes sense anymore. And the reason for that is that the files on the disk, they still have the old regular UIDs. They're still really UID 0, not whatever we mapped that to. So what we need to do now is we need to find a way to recreate this ID shift that we just established with the user namespace also on the file system. So to show this a bit in more detail, to illustrate that further, say we wanted in the user namespace, we wanted our file system to look like this, right? Something that we're used to. We would like to have ID 0 for things that belong to root and some other ID for something that does not belong to root. Whereas on the node, we would like to have everything that from within the user namespace looks like it belongs to root. It would need to sort of refollow this shift. So if we wanted our file system within the user namespace to look like on the left, on the disk, it would need to look like on the right. If we had that ID mapping that's illustrated up there. So 0 maps to 10,000 outside, and 33333 maps to 43333 outside. Now, so basically, we could do this ahead of time, or we could have something that sort of dynamically does this shift, right? So as we try and read those files, we could try and dynamically add this ID on top, or subtract it, depending on from which perspective you see this. And there are different ways of doing that, of going about this. One, and this is one of the most prominent the ones most often used, is Fuse overlay FS. And Fuse overlay FS has a few very nice properties. It works within user namespaces. Not all file systems can be mounted from within user namespaces, only some. There's a special flag on the file system that tells the kernel whether to allow or not allow this. And Fuse, in general, is one that can be mounted within user namespaces. There's very little upfront cost because it's just a mount, and a mount doesn't cost much. But there's a fairly high runtime cost, especially if you're doing a lot of file-heavy operations on that file system, like building software, compiling stuff. And that's because this is a Fuse process. So all file system operations have to go through userland, and you always have that context switch. Another benefit, though, is that it's also not very platform specific. Fuse is widely supported, and Fuse overlay FS is fairly established. Another way this could be done is using so-called overlay FS meta copy. So overlay FS will be known to many of you for its use as Docker graph drivers or containerd snapshotters. And overlay FS supports a mode that's called meta copy, where if you just change the attributes of a file, it's not that the whole file will be copied up, but only something like a tombstone, similar to the whiteouts that happen when you delete something. And that will then contain the updated attributes. So what we could do is we could overlay FS meta copy mount the root file system, and then we could basically run change own on this. And this is exactly where the high upfront cost comes in, because a recursive change own over a potentially large root file system is going to be quite expensive. The runtime cost is is much better than a Fuse overlay FS, but it's still not ideal because nested overlay FS mounts also come with a cost. And in terms of platform specificity, overlay FS is something you can only mount inside a user namespace on Ubuntu, because Ubuntu kernels contain a patch that set this aforementioned flags because they think it's secure enough to do that. And then lastly, speaking of Ubuntu, there is something called shiftfs. And shiftfs is Ubuntu specific and was created for exactly this use case. Its biggest drawback is, one of its biggest drawbacks is that you cannot do that from within the namespace alone. You need to create what's called a mark mount, which basically sort of prepares the shiftfs mount. And this again requires capabilities in the original or beyond what user namespaces can provide. There's very little upfront cost. It's again just a mount. There's also very little runtime cost, exactly because it just does this UID translation and it's implemented entirely in the kernel. But it is fairly platform specific. It will only run on Ubuntu because shiftfs is a Ubuntu specific patch. For Gitpod, we ended up going with shiftfs though, for now. And the reason for that is because primarily we run on Gitpod.io. There's also self-hosted, and I'll talk about that in a moment. And on Gitpod.io, we really care about workspace startup time. So any sort of upfront cost is prohibitive. It's not something that we want. And we have enough control over environment to use Ubuntu on worker nodes, so we can live with the platform specificity. As I said, to use shiftfs, you need to have a privileged operation that is creating that mark mount. And to create this mark mount, we basically do the same thing that we did before with the writing of the mapping, where we call out to workspace daemon, who then does this privileged operation for us. And then once we have that mark mount in place, we can mount our new root file system that we're going to present to the user eventually. And once this new file system is in place, what we're going to do is we're going to pivot root into this new file system. And in essence, what we've done here is we've created a little container runtime. We're stacking up namespaces, we're assembling a root file system, and then we're using pivot root to enter this root file system. In fact, the pivot root implementation that we're using is a literal copy of runc's pivot root. All right, nice, except we cannot mount proc. And the reason we cannot mount proc is that in proc, there is a whole bunch of files that we should not make available to everyone. For example, proc kcore, which basically gives you access to whatever the kernel holds in memory. Or proc sched debug, which gives you information about the scheduler, which in turn leaks details about other namespaces, read containers. So this is not something you want to give potentially arbitrary tenants access to. And the way Kubernetes and others, including runc, solve this is by creating so-called mask mounts. So you don't get just a raw proc, but in reality, you get proc where some files have been mounted over. Like, for example, kcore simply has a bind mount to dev0 put on top. And once you have these mask mounts in place, the kernel will check if you try to mount proc, if you have such masks, and if you do, it will not let you mount proc, because otherwise these masks wouldn't work. You could just simply mount yourself proc and you'd be good. So this is how those masks look like. If you look at in a standard Kubernetes container, for example, you see that on /proc kcore, there's a file mounted on top. So how do we do that? Well, very much the same way like we do all things that require privileges. We call out to workspace daemon and tell it, please mount proc for this PID namespace. And again, we have this PID translation in here that we talked about earlier. Then workspace daemon will make this proc mount for us in the PID namespace of our target, but in its own mount namespace, so that the container cannot see, like the workspace container cannot see it yet. Then it will put all the masks on top that we want. And now we have the problem that we need to move this proc mount into place. Like we need to sort of put this proc mount where the original caller, in this case, supervisor ring 2, expected it to be. And the way we do that is that we use a syscall called opentree, which was introduced in Linux 5.2. And what you can do with opentree is you can create what's called a mount file descriptor from an existing mount within your tree. And then you can use another syscall that was also introduced in 5.2 called move mount, who you pass this file descriptor to, and you can tell it where to move that mount to. And depending on the flags that you use, this tree is copied or moved, and you can really replicate all the operations that you would otherwise do with move or make shared, etc. Or rbind, for example. And the way this works then is this file descriptor that OpenTree will create in the mount file in the mount namespace of workspace daemon is then passed to a process through a Unix pipe that has entered the target mount namespace. Right, so this is how we move this proc mount, including all the masks, into place. So at no point will the caller of this mount proc call have access to /proc without the masks. All right, so at this point, we have a proper user namespace where we're root that has proc mounted, that has a shifted file system. So we could do things like apt-get install, for example. That's awesome. But when we don't have Docker yet, we're not quite there. And what's missing is something that a lot of people have been working on over time. First and foremost, Akihiro Suda, who has done a lot of work in the rootless Docker, rootless container space and containers in general. There also are friends from Kinvolk, without whom none of this work would have been possible, who have been working a lot and are really deeply embedded in the container, Kubernetes, Linux communities. And there's also rootlesscontainers.rs, which is sort of an honorable mention. This is kind of like an index of different technologies around rootless containers. So as said, a lot of, or some parts of some of the ingredients for running Docker within user namespaces already come with Docker. And one of the requirements that Docker has is it assumes it has far-reaching capabilities over its network namespace. And by default in Kubernetes, that's not the case, because the network namespace sits sort of outside our user namespace, right? So if you look at the rings here, the blue one outside, or outside these rings that we have here is the Kubernetes network namespace. So what we do is, we create another network namespace within all the setup that we've done. And then we use a process called slurp for netns to create two Ethernet pairs or two devices using tabtune to get network access outside of this network namespace. And you can think of slurp for netns kind of like Fuse, but for networking. And so it also comes with the same performance trade-off, because now all the networking that happens within this network namespace has to go through a userland process. It's still surprisingly quick, though. And there is work in progress that uses functionality that was introduced in Linux 5.9, specifically seccomp adfd, that would let us overcome these issues. When you start a Docker container, what happens is it will also mount the root file system of that container, including proc. And as we've already established, you cannot simply mount proc in here because proc is masked. But runc will still try and do that. And there are several ways of making this work with this workspace daemon setup. One could, for example, tell Docker to use a custom container runtime, which would basically act as a facade to runc, modify the OCI runtime spec that gets passed to runc, and introduce its own OCI lifecycle hooks, or simply do a bind mount to the proc in the outer namespace. And in fact, the latter is exactly what we've been doing for the past month or so, and it works surprisingly well. What you could also do is use a feature that's called seccomp notify. And what seccomp notify does, this was introduced in Linux 5.0. With seccomp notify, you can load a seccomp filter who, as a result, does not just return something like act erno or act allow, but there's a new action called act notify. And the way this works is when you load this filter, you basically get a file descriptor on which you can call notif receive, and you'll get a request whenever some seccomp filter triggers act notify. And then based on this request, you can either tell the kernel to continue whatever syscall was called, or you can tell the kernel to abort it and return some result or error number, or you can execute that syscall yourself. You can basically act on the caller's behalf and then tell the kernel to tell the original caller that everything went well. So you can basically start to emulate or simulate or intercept syscalls that way. And this is exactly what we're doing when inside of ring 2, someone calls mount proc, then we have a seccomp notify mechanism in place that instead of trying to let the kernel do their proc mount, we'll just call workspace daemon. And then workspace daemon will go through the same mechanism that I just described, where we mount proc and put the masks on top, and then uses the open tree move mount mechanism to move it in place. All right, that was a lot of Linux stuff. So at this point, we actually have Docker and all that fun stuff. So it's demo time. So this is a Gitpod workspace in zoomed way in. Let me just get out of full screen here, right? And so it runs in my browser. It's on Gitpod.io, and I basically started it by, in this case, going to the Gitpod repository, and I just put gitpod.io/hash in front. Right, this is how I got that workspace, and every one of you can do that. Right, all you need is GitHub account, and you're ready to go. This also works with GitLab out of the box, and GitLab even has a button integrated to start Gitpod workspaces, so you don't even have to prefix anything. So to show this off, I'm in this workspace, and here's a fun thing just to have that mentioned. One cool feature of Gitpod is something called pre-builds, and it kind of works like a CI system. So whenever someone pushes a change to the repository, Gitpod will go ahead and already download dependencies. So here, for example, it ran go get on all our Go components, but it would also do that for example, for all yarn stuff, right? And so this is why everything is ready when you open a workspace. This is really neat. I'm always very happy when I see that banana because it means I don't have to go grab a coffee now, waiting for code to build. So back to Docker. First thing we need to do is we need to start the Docker daemon, and we do that by calling sudo docker up. And that is an awesome demo. Good thing I'm already running it. That is why this failed. I'm already running it, right? So otherwise this would have started it, and mental note to myself, we need better error messages in this case. So that means I can now do something like Docker PS. I can interact with Docker as I'm used to, right? So I can just run something. And this is also really neat because these workspaces, they run in the cloud. So basically bandwidth becomes Google data center bandwidth. And I don't know about you, but my internet connection is not that brilliant. So here downloading images really is fun. And so now I'm inside a Docker container. You even have something like port forwarding, right? So if I did something like this, I did port forwarding for 8080, then Gitpod tells me, hey, there's a port here. What do you want to do with this? And at the moment, nothing is listening on it. So if I were to access that, nothing would happen. But if I start a process that serves this, URL, then now I can also access this, right? So this is basically the file listing produced by the file server I just started. This also works with Docker Compose. So here, for example, I already started it, but really it's nothing but a regular Docker Compose example. In fact, it's literally this Docker Compose example. And I just run Docker compose up. There's something available. I open that in my browser, and there's my WordPress, right? Mind you, none of this is running on my local machine. All of this is running in the cloud. All of this I can create, throw away as much as I would like to. Other nice things that you can do with all the work that we've just done, you already see here in the shell, there's something with sudo running. So if I wanted to, for example, call strace on something, right? Strace isn't there. That's not a problem. I can just apt-get it now. Again, speedozo cloud, a lot of funness. So that's sort of the short demo of what this allows. You basically have the full power of Docker available, and also, root. You can do apt-get install, stuff like that. Your file system looks exactly as you would expect it to, or more or less as you would expect it to. Most of the things belong to root. There are some that aren't mapped. This is a technical detail, but by and large, everything behaves as you would think it would. Also, if we look at proc, we see that we have the tempfs proc mounts on top of proc, right? So all the masks are also in place. There's a lot happening in this space. I already mentioned that we're going to get faster networking thanks to seccomp LFD. Also, all this ID shifting on the file system is something that's probably going to move into the kernel as a feature called ID map mounts. Excuse me. And there are first PRs underway to integrate that into containerd. There are also Kubernetes extension proposals that would make user namespaces a first-class feature of Kubernetes. And then there's also seccomp notify, which I'm adding here because it's really quite new and not many people know about it. But it really allows a lot of cool stuff, including those links that give a good introduction. And Kinvolk seccomp agent makes all this work in Kubernetes, unless you integrate it into your own software as we did. So to sum things up, what Gitpod does is it provides ready-to-code dev environments built for and in the cloud. And the way we provided things like root access or Docker in there is using user namespaces. And they're really the key to sort of rootless anything, really. And lastly, none of this would have been possible if it weren't for this awesome community and the great people who do a lot of really great work in this space. Thank you very much.
Okay, thank you, Chris. So I don't think we have questions yet. So basically, it's only new stuff for me, exciting new stuff, and everybody else in the world is knowing it and know how it works. So looks like no questions. But maybe we are waiting some seconds, and maybe somebody out there still has some questions. If not, Chris.
Just ask something. You're missing out on Slack, not Slack. Swag. That's what I meant. You're missing out on swag here.
Yeah.
And there are no conferences that we can attend. So I don't know if you're running out of t-shirts to sleep in. Now is your chance.
Yeah. So basically, until now, I have 4 or 5 Gitpod t-shirts for my own, which is also good. So so it's the time to ask questions. If there aren't any questions, I think Chris and also I also looking at Twitter. If you have a question afterwards, just contact us.
Yeah.
Cool. So thanks, Chris, for your great talk. As always, really great stuff you guys are doing at Gitpod and also contributing.
Pleasure to be here.
Cool. So just let me check one more time if we have any questions.
One thing that I might have forgotten to mention, all of this is open source, right? So I just casually went to the Gitpod repository on GitHub. This is open source. So feel free to poke around, have a look. Also, shameless plug, we are hiring. And we're looking for cool people. Go to gitpod.io/careers. There's a whole host of open positions. Have a look. If you're looking for a really incredible team spread all over the world, we're fully remote. Go chat us up.
Cool. Okay, so with this, everyone, thanks for joining, and yeah, see you next time. Bye bye.
Bye bye.